Alright, welcome back. It's lesson 10.3. In this video, we're going to talk about something called polar area. And there is a formula that's just in this box that you need to memorize. But before I actually talk about it, I want to show you how this formula came to be. Now, to do that, I'm going to have to go back to your pre-calculus days. And hopefully you remember this lovely shape. Yes, it's a circle. And if I were to ask you to find a sector, let's see if I can draw it here, like a wedge of the circle, right? And I ask you to find, hey, that sector, it's scooped out by some angle theta. And I could say to you, look, can you find the ratio of the area of that sector to the entire area of the circle? If you want to find the ratio, you're like, oh, I know, it's the sector area. That's the wedge in blue. I guess you're dividing it by the area of the circle. What's the area of a circle again? You got it, pi r squared. And this is the ratio of the area of the sector, the wedge, to the circle's area. I can also do the same similar ratio with the actual angle, and I called that sector area angle theta, and the entire circle has an angle of, yes, I hope you remember, 2 pi radians. So this is an equivalent ratio. Now, our goal here is to find the actual sector area. Okay, I want you to find the area of that wedge. So if I were to now solve for sector area, I will take that pi r squared and move it to the right-hand side, multiplying by pi r squared. And then notice the pi's divide each other out, and you're left with 1/2 theta r squared, or 1/2 r squared, and timesing it by theta, where theta is the angle in radians. So this is what you hopefully learned in pre-calculus 12. But notice how similar this is to our actual formula for polar area. 1/2 is there, it's a constant. The r squared is there. But now instead of a theta, we replace theta with this d theta, and then from A to B. So really what I'm saying is you're sweeping out an angle starting at A and going to B, and that angle will help you figure out the area of that sector. Okay? So using this idea now, let's see if we can do example number 1. Find the area of one petal of the curve of r equals 3 cos 3 theta. Okay, so you might want to draw this out, and we did lots of drawings of polar graphs in the previous lesson. If you're curious how we can do this, I always like thinking about drawing it in rectilinear form first. So, thinking about y equals 3 cosine 3x. And then I think, yeah, amplitude 3. Interestingly enough, that we have a period here, in this case of 2 pi over 3, because that 3 is a horizontal compression by a factor of 1/3. So like 2 pi over 3, 4 pi over 3, and then 6 pi over 3 is 2 pi. And then, yeah, we're going to, I guess, graph this out. So, 1, 2, 3. Okay. And if you wanted to think about how that transfers to the polar graph, I guess we're looking at, starting at 3 when the theta equals to 0, then going closer and closer to 0, I guess it will be something like, Now you might be thinking, how do I know when it goes back to the origin? Where are these x-intercepts? Yes, you have to find them. Yes, how can you find them? Well, maybe that's when you let the r value equals to 0. So we can let r equals 0 to find out when the angle theta actually has the r, or the radius, being equal to 0. All this stuff from pre-calculus that you need to now solve. Mm-hmm. Inverse cos, what is that? I think that's pi over 2, right? Or 3 pi over 2? Yeah. Now remember, that's 3 theta, so you're not done here, right? You gotta keep going. Theta equals to what? Or 3 theta equals to pi over 2, so therefore theta equals pi over 6. And also 3 theta equals to 3 pi over 2, which means theta equals to pi over 2. So yes, I know that I come around, whoop, and then I'll come back to r equals 0 when pi over 6 is the angle. So if you really think about me drawing this, this is the angle pi over 6. Okay? And if I keep continuing to draw this lovely picture, hopefully you'll visualize that it looks something like this. Whee! And then back around. Okay, so this is the one where there's 3 petals, and technically all the petals are the same size, so I didn't really draw very well. Okay, but they are all the same size. So really, I'm asking you for the area of one petal of the curve, and so you don't. It doesn't matter which one you choose, but I'm thinking I'm going to do this one here. I think it's a little bit easier. Why do I think it's easier? Because if I want to find the area of that petal, maybe I don't even find the area of the whole petal. Maybe what I do is just find the area of this part that I'm highlighting here in green. Why just that part? Well, because this is some polar area that goes from theta equal to 0 to pi over 6. So I'm sweeping out the area of this curve from 0 to pi over 6. Okay? That equals to half of the actual petal. So a full petal would be double of them. So let me just say this. The area is equal to, and I'm going to say now using the formula, look at the formula, polar area, 1/2 the integral from 0 to pi over 6 of r squared. So r is 3 cosine 3 theta, all squared. And then don't forget the d theta. And if you leave it like that, that's only the green part. Yes, I want to double it to find one petal. So once again, this is just the area of half a petal, the part that I highlighted here in green. And yes, you're going to have to multiply this by 2 to double it to get the full petal. Okay? So once again, I chose to go from 0 to pi over 6, but you could have chose something else. I just thought, hey, this is the easier one. Okay. In order for you to now evaluate this, yes, you're going to have to use a graphing calculator. So the 1/2 and the 2, I guess that simplifies to 1. And ultimately now, you need to use the graphing calculator to actually calculate this ugly integral. So go ahead and do that. Here's my graphing calculator. Turn it on. Remember how to do this? FNINT. So math number 9, I believe. Yep. And we're going to type this in. So 3 cos 3x. Okay, don't forget I need this all to be squared, so I think I should have actually put an extra bracket here. Squared, comma, x, the variable, and then from 0 to pi over 6. And I'm sure this will be an ugly decimal. Yeah, 2.356. And that is your answer. Okay. So putting together lots of different things here to do this one question. Putting together your knowledge about trig, putting together your knowledge about graphs, oh boy, and using the formula for polar area. Okay? All right, on to example number 2. You might also need to find the intersection of polar graphs, because remember how we found those area questions, area between curves? I can do the same thing here with polar graphs. So here I have the question, find the points of intersection of the graph of 1 minus 2 cos theta and r equals to 1. So remember, if I were to graph this out, 1 minus 2 cos theta, back in my pre-calculus days, maybe I'll write this as -2 cosine theta plus 1. That would be what? Here's the graph -2 cos theta, right? But then I have a +1, so I have to shift it up 1 unit, whee, like this perhaps. Okay. And if you're thinking about how that translates into a graph, I'm thinking it starts at -1. So I'll start right here. And then it gets closer and closer to 0 somehow. And then it goes farther and farther away. All the way to, I think, 3. And then back around somehow. And ending up with this. Okay. Now, maybe if I wanted something nicer, let's try to make this even more accurate here. I think it actually goes through 1. Like that. Okay. Boom. How about like that? Ah, that still doesn't look very nice. The quest to try to get a nice drawing. How about like this? Okay. All right, and then how about r equals 1? Let's spend some time doing that now. R equals to 1, that's a circle with radius 1. So you might already see the points of intersection, right? But let me try to prove this algebraically to you. So how do we find intersection points? We let the two functions equal each other since they both equal to r. And if you do this, 2 cosine theta equals to 0, or cosine theta equals 0, you bet. And therefore, we did this before, theta is just pi over 2, or also 3 pi over 2. And that makes sense because at pi over 2, we are looking at this angle up here, and it looks like we have an intersection point right here. So what would be the coordinates of r comma theta? Well, r always must be equal to 1, since r equals to 1, and our theta is pi over 2. That's awesome. And then 3 pi over 2 is an angle going down here like this. That's awesome. That's this intersection point. And once again, our theta in this case will be r is 1. Our angle is 3 pi over 2. But you might be thinking, I see another intersection point over here. How come I couldn't find that graphic or algebraically? Well, remember, there's another way to describe the circle with radius 1. I could also describe this as r equals to -1. It's the same shape, right? So if I were now to solve this, 2 equals -2 cos theta equals to 1. Notice what I have here. Ah, yes, this is when theta equals to 0 radians. And in this case then, r theta, yes, even though the angle is 0, but because r is -1, we're going into the negative direction. So yeah, that point is actually -1 comma 0. Okay? So that's how you can find the intersection of that point as well. Ooh, crazy, crazy, crazy. Now, once again, why are we doing intersection of polar graphs? Because my last two examples here are area between curve questions. Okay, so your goal here is to actually find the area of the region that is common to the two regions bounded by these two curves. Oh boy. So let's take a look. We have here. Dun, dun, dun. How do I graph this out? -6 cos theta. Yes, I hope you realize that that's just a circle. When theta equals to 0, you are at -6. And this would be a circle of radius 3. So here we go. Okay, that's r equals -6 cos theta. And for the other one, r equals 2 minus 2 cos theta. Hopefully you can visualize that. Okay, once again, if you want to rewrite this as y equals 2 minus 2 cos theta and graph it out, that would be what? Negative 2 cos theta looks like this. Whoop, right? And then adding 2 to that would be like this. Okay, so you can go ahead and think about that. Starting at 0. And you are, what are you doing here? 2 minus 2 cos theta. I guess, yeah, you are just going and making the values positive like this. Doo-doo-doo. I'm not too sure, but it'll probably go something like this, all the way to 4 at pi, and then come back around, something like this. That's the heart-shaped graph. Okay? Now, what is the area that is common to the two regions? It is this part in here. Notice that there is some beautiful symmetry as well. So perhaps instead of doing the whole thing like this, I can just do half and then double it, because that might make life a little bit easier for me. But I still need to know where the two graphs intersect, because I need to find that angle. Okay? So how do I find the intersection points? Hey, that's what we just did earlier. Same kind of idea. Let's make those two equations, because they both equal to r, equal to each other. I'll quickly do some algebra to solve. Hopefully you can do this yourself as well. Cosine theta equals negative 1/2. What are my angles here? This is the special angle. I believe it's 2 pi over 3. And the other one is 4 pi over 3. So yeah, I think what you'll see here is this is 2 pi over 3. And this other intersection point down here, 4 pi over 3. Okay. Now, once again, our goal is to find the area. Okay. So that's common between the two regions. So maybe I'll say, let's find the common area. And that is equal to this top area, I'll say, times 2, right? Because I need to double it. Now the trick here is, how do I find the top area? Okay. Notice here that the top area has two different graphs. That red portion, okay, I'm going to highlight this. Let me do this. Top area times 2. I did not want to erase that. That is correct. But what I want to say is this. I want to show you this red area. Okay? Because that red area, okay, is found by taking the integral of the red function, negative 6 cos theta, right? That one squared, with of course a 1/2 in front, and a d theta. And notice that the angle that I'm starting to do the rotation from is right here, which would be pi over 2 for the graph in red. Okay, so remember, pi over 2, and I'm going to stop at 2 pi over 3. So that takes care of that region that I just highlighted in red. Okay, that is only part of the top, though. So then there's this other region that I'm going to shade in blue now. How do I find this area here? Well, notice the curve I'm using is this blue curve now. So I'm going to have to add to this plus 1/2 the integral of, I'm using the blue equation, 2 minus 2 cos theta, d theta. And this time, look, I'm going from 2 pi over 3 all the way to pi. Because this angle here would be pi. And so the combination of these two things is my top function. So this whole thing here is the top. Wow. And then, yes, you'll need to multiply by 2. Okay. Now, once again, I forgot something. It's half, and this is a common mistake that people make. They just think about it's half, and then r, don't forget, squared. Okay. and then times it by 2. Now, to do this, I would ask you to use your graphing calculator again. Punch this out, all right, and get the answer. I've already done it, and because I don't want this video to be like 45 minutes long, I'll just tell you the answer right now. This is 15.708. But I hope you can punch this out yourself as well, okay? The goal here, once again, is to really see how we can create these areas, okay, by sweeping out angles given a particular R or function. Okay, one more. Find the area between the loops, of this function, R equals 2, bracket 1 plus 2 sine theta. So always with these, I like to have visuals. If you really can't draw this out right away yourself, then if you're allowed a graphing calculator for this question, by all means just type it in. I will change my mode to polar. R equals 2 bracket 1 plus 2 sine theta. Let's see where this inner loop thing is going to be. Graph it out. Oops, bad graph. Bad window. Oh, there's an interesting thing. Oh, let me change my window. I need some negative x's. Probably need some more positive y. Let's graph. Here we go. Oh, inner loop. Interesting, 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 interesting. So, once again, here's my equation. Graph it out. Notice it started at 0, and then it went like this. Whoop. And it went all the way up to what? 1, 2, 3, 4, 5, 6. It went all the way to 6. Wow, all the way to 6. And then it came back down around. And then here's where it did that weird inner loop, right? We went whoop, whoop, whoop. Craziness. Craziness. Okay, so find the area between the loops. So what I'm saying is I want you to find the area of this. All of this. And once again, I hope we can use symmetry to help us out. Okay. I think what I need to do, though, is to really show that perhaps instead of doing the full thing, I can just do half. This part, oops, undo. This part here. Okay. Which really means, though, I really should be taking the area of that whole part that's up to here. Okay. So that would actually include this little piece here. And I need to then subtract away that small piece in blue. And that will give me half of the area between the loops, right? And then really then, if I want the area between the loops, I would take that and double it. Does that make sense so far? Okay, if so, that's great. Now we just have to figure out how to find the area of those two shapes. So I'm looking at this lovely picture and I'm thinking, I think we need to figure out what thetas give you this r being equal to 0. So if I were to make 2 bracket 1 plus 2 sine theta equal to 0 and solve, I'm really going to have what? 1 plus 2 sine theta equals 0, 2 sine theta equals negative 1. Let me get some more space here. Oh, sine theta equals negative 1/2. And yes, using my pre-calculus 12 knowledge, I think 7 pi over 6 and also 11 pi over 6. So if you think about me coming along this curve and then coming right about here, notice that this angle will be 7 pi over 6. If I keep going around and around and around to the other side, this angle over here would be 11 pi over 6, which makes sense by the drawing. Okay, that's going to help. because that 7 pi over 6 is where my yellow region actually stops. Okay, so the question I have for you is, where does my yellow region begin? Boop, 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 boop. Yeah, this is just pi over 2. So for the area of the loop in yellow, that includes that little bit in blue, so this shape here, I know that it's going to be 1/2 the integral from pi over 2 to 7 pi over 6. Of what function? Yes, it's 2 bracket 1 plus 2 sine theta, and this whole thing is squared. Don't forget the square, and then d theta. Okay, that's good. Now, to tackle the next part here, the one that small little region in blue, we have to figure out once again where we're starting and ending. Okay? So, if we were to look at the part that I shaded, we know that it ends at 11 pi over 6. But the question is, where does it start? So it starts here, but this angle is not pi over 2. This one is actually going this opposite way. That would be actually 3 pi over 2. So once again, that's because that has a radius that's negative. So you go in the opposite direction. So if we're looking at that region, it would be the integral from the starting value is 3 pi over 2. The ending value is 11 pi over 6. And once again, the function is still 2 bracket 1 plus 2 sine theta all squared d theta. Okay? And then this whole thing gets multiplied by 2. Okay? Wow. 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 Crazy, crazy stuff. And once again, I'm not going to ask you to do this because I think, sorry, well, I will ask you to do this. I think you should try it. I'm just not going to show it to you because I don't want this video to be that long once again. But I believe the answer for this question will be 33.351. Okay? So there you have it. This is tricky stuff. I'm going to ask you please to work on the assignment, and you need some practice here. Okay? The key thing is to make sure you set up the equation correctly. Okay? Figuring out the correct angles you're sweeping. That is the key. All right, we're done for today.